So this video is the third in a series of videos introducing differential equations. In this video, I'm going to start describing what we call qualitative methods. So in some courses, you'll focus entirely on how to solve a differential equation, but you don't actually have to solve a DE, a differential equation, in order to find out information about its solutions. By solving a differential equation, you actually get a function, a formula for how the solution behaves or what it looks like. And that's not necessary. You can get a lot of information using these qualitative methods. So this is a first qualitative method. So solving is not required. So we're not going to get necessarily a formula for the solution in the end, but we might be able to roughly graph it. That's the idea. That's the goal here. Okay, so let's do an example right off. We have an idea so far of what differential equations are like. And let's start with, let's say, the differential equation dy dt equal to y. So we've already talked about what a solution to this differential equation looks like. And I'll put it on the side, but keep in mind that we don't need this solution in order to use this method, but it'll help us to understand the method. So here y of t is equal to e to the 2t. Okay, that's the solution. And c could be any constant. Okay, so before I get into the slope field method, let me just do a little bit of manipulating of this equation so we can see how solutions to this equation behave. And what I mean by that is I want to rearrange it and see how all the solutions relate to each other. This expression makes it seem like all of the solutions are basically e to the 2t, and so you have curves like this, but this one might have a c value of 2 e to the 2t, and another one might have 3 e to the 2t. And it looks like all these solutions are related by being vertically scaled versions of one another. So that's one way of seeing an exponential function. But exponential functions are kind of special in that this interpretation can be sort of turned around or flipped. And let me show you. So if c is positive, let's just assume c is positive, then we can rewrite c as e to the log c. Right? Because e to the log of anything is just that same thing. Okay? And then I multiply that by e to the 2t. But now I have two bases that are the same, so I have e to the 2t plus log c. And now I can factor out the 2, and I get t plus log c all divided by 2 in brackets. And what this shows is that instead of thinking of all these solutions as being vertical scalar multiples of one another, where you get multiplied by 2, multiplied by 3, this shows that every exponential function is a horizontal shift of another. So every one of the solutions is a horizontal shift, right? This is a shift by, if c is positive, let's see, so log of c might be positive or negative. Depending on whether this is positive or negative, this is going to be the function e to the 2t shifted to the right or to the left. So you can think about this form as being a vertical scale, multiplying by c bigger and bigger or smaller and smaller. And then this form here makes it seem like, oh wait, they're horizontal shifts, not vertical multiples. So this form is going to be useful for thinking about the graph that I'm about to draw. And now if c is equal to a negative value, you can still do this. If c is negative, then you can replace the e to the log c by minus e to the log of minus c. And the same sort of calculation will go through. But I'll just leave that to you if you want to see how that works. Okay, so let's get to the method here. So I'm going to draw an axis here for t, for time, and an axis here for the y variable. And now I'm going to put in these functions. So here's the exponential function growing. And I want these to look exactly the same horizontal shifts of each other as I just described. So I'm going to put them in looking exactly the same by pasting them. And then I'll also have negative values. I'm not thrilled with that shape. Hold on, let me try that again. Still awkward, hard to go down. Okay, so all of these will also be horizontal shifts of one another. And so this is what the whole collection of solutions will look like. Okay, so now what I want to do is I want to come up with a way of figuring out that this is what the solutions look like without actually having the solutions. So let's just notice, because they're all horizontal shifts of one another, the slope here and the slope here and the slope here are all the same. And then if I go a little higher in the y direction, so this is all at, let's say, y equal 1, the slope along there is all going to be 1. Oh, no, sorry, it's going to be 2. I have 2 times y, right? Because this says that the slope of the function y of t is going to be twice the y value at any moment. So if the y value is 1, the slope will be 2. So all these slopes are 2. And then if I go up to 2, all the slopes there will be 4. And if I go up to 3, then all the slopes at this point, 3 at this height, will all be the same. They'll all be a slope of 6. So I didn't need the exponential function there. This expression already told me that. If you tell me the height, doesn't matter where it is in time, the slope of the function going through there has to be 2 times the height. So if I were here where I didn't draw one of those, I still know that this would have a slope of 4. And if I was at this point would have a slope of 6. So I can do that on this bottom end as well. And so the entire collection of little red lines this is called a slope field. And it's important, you don't need the solutions drawn in there. We could erase the blue and we could still come up with all those red curves. Okay, so that's what we call a slope field. Okay, so now let's try and figure out what we can do with this without knowing what the solutions are. So I'm going to give a function here that's a little bit more complicated. So imagine dy dt is equal to, so I think in the previous video, I talked about this example, a non-autonomous function where we have the slope changes depending on the position and the time. And so here in the exponential case, it only depended on y. And we got these slope fields that were all the same steepness in horizontal bands. But we can have a non-autonomous equation that has, let's say, I'm going to take a simpler version of the one that I had there. This is just going to be 1 plus cosine of t minus y. Okay, so let's try and draw the red lines without knowing what the solutions look like. And you'll notice here that because there's a dependence on t, because this is non-autonomous, we're not going to be able to shift the solutions horizontally the way we were able to do that here, right? Because the slopes will be different at different times as well as at different y values. Okay, so here we have our t-axis and our y-axis. And now I'm going to do the same thing as I did before. I'm going to go for 1, 2, and 3. And then see what happens. And in this direction, I'm going to go out to 2 pi pi halfway, and pi over 2, and 3 pi over 2, and 0. Okay, so so let's build this in pieces. At y equal 1, we know that, let's see, y equal 1 and t equals 0. We have, so that's, let's say right here, we have y is 1 and t is 0, so we have 1 plus cos of 0 is 1, so that's 2, minus 1 is 1. So we have a slope of 1 at the start. Now how does that change if I go horizontally? By the time I get to pi over 2, so if I plug in pi over 2 to the cosine function, that gives me 0 here. So this is 1 plus 0 minus, let's stay at the same height, 1, and I get 0 there. So the slope here is 0. Then let's try pi, go a little bit further. By the time I get to pi, the cos of pi is minus 1. So we have 1 minus 1 minus 1. These cancel and I'm left with minus 1. So now my slope has flipped. And you see, it should be clear now that if I did find a solution that went through this point, I can't just slide this horizontally and still satisfy the differential equation because the slopes will be wrong. And so we don't have that nice shifting property that we had back here. Okay, well that's fine, but we can still build our solution out, or at least the slope field for it. And now at 3 pi over 2, we're going to be back at the same value as we were at pi over 2. It's going to be 0 again, and now that means that the slope will be 1 minus 0, or 1 plus 0 minus 1 here, so we get a 0 slope again. And then at 2 pi, we'll be back to where we started with a slope of 1. Because by the time we get to 2 pi, the cosine is 1, and we get 1 plus 1 minus 1, and that's 1. Okay, so that's the first row. Now what happens if we go up to y equal 2? Well, all of these slopes will be the same, except now I'm subtracting off 2 instead of 1. So anytime I had a slope of 1, I'm going to drop it down to 0. Anytime I had a slope of 0, it's going to go to minus 1. So at 2, I'm going to have a flat line, because it's 1 less than it was at the 1. And this 0 slope is going to become a minus 1 slope. This minus 1 slope is going to become a minus 2 slope. This 0 slope is going to be a minus 1 slope, and this 1 slope is going to be a 0 slope. And then we can continue. If we go up to 3, y equal 3, we're subtracting yet again 1 more. So now we had a slope of 1 and then 0, and now it's going to be minus 1. And then here we had a slope of 0, minus 1, minus 2. And here we had a slope of minus 1, minus 2, minus 3. And then here we have a slope of 0, minus 1, minus 2. And here we had a slope of 1, 0, minus 1. And so now the problem is kind of the opposite of what we did over here. Here we had these solutions, and we just used their little tangent lines to represent their slopes, and that gave us the slope field. Here we have the slope field. Now what we need to do is we need to find curves that go through this slope field so that the curve has always got these little line segments tangent to them. And so if I start off, let's say, here at 1, and I'll do this with the little highlighter tool first. So here I can see clearly that I'm going to be rising with a slope of 1, and that means I'm going to go into this region. But as soon as I rise up here, you can see that the surrounding ones have lower slope. So it's going to turn, and now I'm headed between these two, and these two I have to sort of fill in my head here with a smooth sort of gradation from the steeper slope here to the 0 slope here, and I'm going to have to follow one of those little lines in there. And so it's going to come around like here, and now it's got to go down, and so on. So I'm going to have some curve, and if you fill in more of them than I have here, you'll find that this thing has to do something like this. And you can see clearly that this doesn't shuffle sideways nicely like we had before, and that's what I was kind of predicting when I said that the slopes will change horizontally now. Anyway, so this is a simple example of a slope field. It's a little bit hard to see what's going on in this case because it's hard for me to draw so many slope field elements and fill through them. So what I've done is I have, 2 pages down, I guess, I have a slightly different equation. It's almost the same equation. Let me fix that. Whoops, I wrote over. Oh, this is going to be tricky, isn't it? Let's see if I can do this without getting rid of everything. Let me patch that up again so it doesn't distract. So this should be a T here. Oops. Okay, so now we have a slightly more complicated differential equation. I've put a 3 in front of the cosine expression. So I have a 3 here, and now instead of 1 plus cosine of x, I have cosine of t over 2. The only reason I did that is because I wanted to get a nice grid of slope field elements that was easy to see lots of what was happening at once, and these changes here and here allowed me to compress and make it more complicated to do to figure out the slope field by hand, but it makes it easier once you've generated automatically to actually fill it in. Okay, so what I've done here is I've chosen 3 different initial conditions to try out, these 3 dots, and I want to see how it behaves. So one thing to keep in mind is, so whenever we start, let's start with this one down here. So if we start over here, what do we want? We want to have the solution here is going to start in this direction, and it's going to move up, and now I have to fill in, because I'm in between these two, I have to fill in between them, and you can see it goes a little bit lower slope. So it's gradually moving a little lower like that. So when I fill it in, I have to move it lower slope, and then it's going to go really close to the green one. And then here again, I've got to do all sorts of filling in of slopes in my head. So let's say between these two, they drop like that, and between these two, it was like this. These are actually pretty similar. And so through here, it's going to go something like this. And now here, it's got to come up. And I mean, a lot of this you have to just on the fly kind of fill in your head. Like between these ones, there should be something like this going on. So I'm going to come through these ones and should do something like this. Okay, so that's our first solution curve. And then our next one, let's go all the way down to this one at the bottom. Here, we're going to start steep, but as we move up, we're going to move away from these slope elements here and get into the middle, but these are all very close to parallel, so they kind of move, the solution should move straight up like this. And now they start to curve away, and now you can see there's a pretty big difference between, let's say, this one and this one. Well, not a big difference, but by the time I get up here, these ones are wildly different, so I have to sort of fill some things in my head. And so maybe it goes like this. But you can see once I get here, I kind of get trapped. I can't cross any of these, right? I have to go parallel to them as I go by them, and it kind of traps me in. And they kind of collect around, it turns out they collect around a cosine curve, and it's not unrelated to this cosine function here. So if we start up at this one, we have to come down, and it's going to do a similar thing. It's going to collapse down, and it's going to follow this curve as well. And so, so this is how we fill in slope fields with approximate solution functions. So we've never calculated these, right? I don't know what the formula is for this curve here or for this curve here, but I know that it has to be close to a solution because I'm trying my best to follow the rule of having the slope of this be determined by this formula, and each one of these little line segments is a tangent line whose slope satisfies this formula. Okay, so that is everything I wanted to say. Oh, that's not everything I wanted to say about slope fields. Let's see, how are we for time? you know what, I may stop this video here and do another one where I'm going to talk about slope fields and use them to sort of describe or define what a phase line is.